Hello, everyone, and welcome to part 20 of Python programming lecture series. This is Ramprasad Pujari. In this session, our goal is to understand the challenges in machine learning. More emphasis will be given to the two concepts, underfitting and overfitting, and how you can address them. Firstly, we require a data set, so we can create a data set which resembles this example. This is an ideal data distribution for demonstrating underfitting and overfitting. This pattern can be generated using cosine function of NumPy library, and this in fact is 3/4 cycle of a cosine wave. Okay, so we are given the training samples. The next step is to build a machine learning model which has a learning function that accurately fits the data as shown here. You can see that in orange color line that is a true function. So we need to build a model which resembles this learning function. So this looks like a polynomial function. So you can't have a linear function. So linear function will give you a straight line when you have only one feature x. So you need to have a learning function which resembles this shape, that is a polynomial shape. Can we use the linear regression model to fit a polynomial function? Because we understood that this learning function is a polynomial function. So we can't use just a linear regression model here because linear regression model gives us a learning function y equal to mx plus c when you have only one feature x. And y equal to mx plus c is a straight line. You can't have this particular shape. So you can't use linear regression model alone. But you can modify the linear regression model. We can, with a slight twist, we can get a polynomial function. So in order to get a polynomial function, polynomial learning function, so we need to follow this two-step process. The step one, we will transform our x is nothing but the feature. We have only one feature x. We will transform it to get polynomial features. Now we can do this using scikit-learn.preprocessing. Under that, we have a class called polynomial features. So we can use this class to transform x to polynomial feature. That is the first step in this case. And this step is called as feature transform, or this technique is called as feature transform. It can also be called as feature engineering. Now, once you get the polynomial feature, then polynomial features can be fed as an input to the linear regression model, and so that will give us a polynomial function. So here you can see, though you have used the linear regression model, you end up getting a polynomial function. The complexity of the polynomial function depends on the degree of the polynomial, which is n in this case. If n equal to 1, then you will have only two terms, a1x plus a naught, which is like a straight line equation, mx plus c. A1 is the slope and a naught is the intercept. As the degree of polynomial increases, the complexity of the model also increases. So let us take two different cases. If degree equal to 1, you end up getting a straight line function, okay, which is just a very simple linear regression model. But when degree, let us say 25 or 30, then you will have a very complex polynomial function with large number of coefficients. So you will have 31 parameters. Out of them, 30 will be the coefficients, and this one will be the intercept or the constant. So complexity of this model depends on the degree of the polynomial. So later we will see that what happens when you increase the complexity of the model, what happens to the learning function. Before jumping into the practical session, let us look at these three cases. The first case is called as underfitting, second case is overfitting, and the third one is a good fit. The first case, when the degree of the polynomial is 1, so you end up getting a straight line function which is of the form y equal to mx plus c, as we saw in the last slide. So this particular function does not fit the data properly. The reason is this is very simple model. The learning function is very simple, so you can't use it. The second thing is overfitting case, where you can see that the learning function even fits the noise in the data set. It captures the noise in the data set. And this is the case when degree of the polynomial is very high. In this case, the degree of the polynomial is 30. So when the degree of the polynomial is very high, the complexity of the model also increases. It's very high because the learning function is very complex. So because of that, if it even picks up the noise in the data set. Now the problem with this is this particular function cannot be used for performing predictions on a new data set which a model has not seen. So there, this will fail. So overfitting and underfitting are the two important concepts in machine learning, and we should mitigate them. Reason for underfitting is the model is very simpler, so you need to increase the complexity of the model, and model should not be very complex that it even picks up the noise like this, or it memorizes those coefficients value. So we need a model which is not very simple and not very complex, which has a function something like this, and this is called as a good fit. Now this is the case when the degree of the polynomial is 4. Now from this discussion we understand that when we design a model, the model should not be very simple, that it doesn't fit to the data, training data itself, and it should not be very complex, that it also picks up the noise in the data. We need a model which is not very simple and not very complex also. So if there is a overfitting case, then there are some strategies to mitigate them. There is something called as a regularization, and that can reduce the complexity of the model. So we'll discuss about other concepts in the next session. Now we will jump to the demonstration session. This is the most important part of this session, practical session. I'm using Google Colab for this exercise. You can use any other Python IDE. Very first step is to import the necessary libraries. So I need few libraries for this. Matplotlib is one of the library for plotting. Then I need a NumPy library, as you can see here. There's a NumPy library. Then from scikit-learn, I need to import a linear regression class as well as polynomial features. Because as I explained earlier, we follow two-step process. First, we need to transform the features into a polynomial features. So we need polynomial features class. And once you get the polynomial features, we are going to train the linear regression model on this polynomial features. So these are the two different classes we need from sklearn. So once you import necessary libraries, we need to generate the labeled data. When I say labeled data, we need x and the corresponding y value. 50 training samples, so x will have 50 values. Sort function can be used here. Y will be depends on the shape of the data. So if you look at this particular thing, so this is three-fourth of a three-fourth cycle of a cosine wave. So we can generate this using a cos function, cos of 1.5 pi into x. So numpy function can be used and you get this y value. So once you have x and y, you can display this as I have displayed here. X axis is a feature and y axis is a target variable. Now the real data set always will have some amount of noise. Now, in order to introduce noise to this data set, we can use a random noise function of NumPy. You can see that a small amount of noise, maybe 10% of the noise will be added to this, and that will give us this particular data set. It's the same data, original data, with a noise embedded in it. So we are going to use this labeled data set for building our model. Once you have the data set, now we have to focus on the learning function that we need. We need to focus on the model. What we understand here is this is the data distribution. Now, if you want a model which can accurately fit to this data, our true function should be of this form, which looks like this orange color, which is a true function. We need a model with a learning function which looks like this. This is like a polynomial function. Let's look at the two-step process that we discussed earlier. The first step is to transform the features into polynomial features, followed by a linear regression model. So you can see that this is a polynomial function. We need a learning function which is having this expression, and this is the case for degree equal to 3, and this is the case for degree equal to 1. And when as degree increases, degree of the polynomial increases, this polynomial function becomes more and more complex. First case, case 1 is underfitting. We take degree equal to 1, degree of the polynomial is 1, and we initialize the polynomial features with degree equal to 1. Then we'll use this fit transform function, and x will be the input. So you will reshape to add a new axis to it. So what this step 1 does is it actually transforms x to x polynomial, so you get polynomial features. Now once you have this polynomial features, we will use these polynomial features to fit a linear regression function. So you can see that this is our model, linear regression model, but the input will be the polynomial features instead of x. So step 1 and step 2 are done. We'll plot this function. We'll want to see how a learning function looks like this. So let us just plot this function. So you can see that I'm using matplotlib function for this. I have a separate video on matplotlib. You can watch that video. So as you can see here, when degree equal to 1, degree of the polynomial is 1, you end up getting a straight line function, which is of the form y equal to mx plus c. This particular case is called underfitting, where your learning function does not fit to the training data. That is because the model is very, very simple. The second case, will move on to the second case, which is nothing but overfitting case. So here we take the degree of the polynomial as 30. Again, it's a two-step process. First, you transform the feature to a polynomial feature using this class, followed by a linear regression model. So you train the model using a fit function. So only difference between the first case and the second case is that here the degree of the polynomial is high. So your polynomial expression will have 31 terms, including the intercept or bias. And so let me just run this particular cell, and you can see that this will be my learning function. And if you look at the learning function, what we understand that it actually even captures the noise in the training data. Now, the problem with this performs very well on the training data, but when you try to use this function to predict on a new data set, then this will fail. This cannot, perform well. So that is a drawback of a model which overfits. So this is the second case, overfitting case. We'll look at the third case where the degree of the polynomial is 3 in this case, and again two-step process is followed here. So let me just run this cell, and you can see that when degree of the polynomial is 3, not very high or not very low, so you can see that it accurately fits to the underlying data. So let us now conclude this session. From this discussion, we understood that the overfitting occurs when a model is excessively complex and it fits too closely to the training data. So the problem with this, it does not perform well on new unseen data or a test data. Underfitting happens when a model is too simple and it cannot capture the underlying patterns in the training data. So because of that, it doesn't perform well on training as well as test data. Good fit implies that the model strikes a balance between underfitting and overfitting, where the model is not too simple and not too complex also. It generalizes well to new data, so that means it performs well on both training as well as test data set.